Hi, everybody. Chapter 15. All right, chapter 15 is entitled Kinetic Theory, but it really should be Kinetic Theory of Gases. And the reason why is when you look at solids and liquids, the particles that make up those solids and liquids, the atoms, the molecules, they're so close together and so in contact, they're in contact with each other. And so, therefore, the phenomena of things like exchanging heat to create temperature or pressure is so similar that there's not much of a distinction. In other words, if you were to heat up a liquid or a solid, the particles start to move faster, they vibrate more, they collide with each other more, and if you heat them up enough, a solid will turn into a liquid. Okay, but the only difference between a solid and a liquid is that in a solid, the particles are touching each other, but they can't move around into different positions. Whereas a liquid has the ability to pour and to flow. So the particles have to touch each other in a liquid, but they're able to slide over top of each other. So when you talk about temperature, which is collisions among the particles that exchange heat energy, the particles are already touching each other, and it's very easy to translate heat. For pressure, when we think of pressure of a liquid or a solid, it's just a matter of spreading that liquid and solid out to create low pressure. The pressure itself is really the weight of the object. But with gases, it's totally different. For instance, if you had a stapler that was composed of gas particles, and let's say it was summer and your air conditioning broke, and the temperature in the room went up 20 degrees Celsius. For a liquid and a solid, the objects in your house, yeah, they would expand because of the additional heat, but you wouldn't walk into a room and notice any difference in the size. The change in the temperature of the room isn't so much that it would melt the objects or cause the objects to boil. So, the door might stick a little bit in the door frame because of the expansion of the door, but it's not something that's going to be noticeable. Whereas if you had a stapler made out of gas and the heat went up 20 degrees Celsius, now the stapler is about 4 times larger. It would be 4 times longer, 4 times higher, 4 times wider. If all the objects were made out of gas particles instead of liquids or solids, even you would expand. So on a hot day, for instance, Mr. Burnett made out of gas particles would now, instead of being 6 feet tall, I'd be 24 feet tall and huge. So the phenomena of gases versus liquids and solids is so different that in your textbook, when you're doing introductory chemistry, they devote separate chapters just to gases as opposed to liquids and solids. And that's really what we're going to focus on with the kinetic theory. So the kinetic theory you've had before, you had it back in middle school where you didn't learn anything. But I'm going to go over the premises. First of all, with kinetic theory in this chapter, they want to talk about particles moving around and creating collisions. And there are two types of collisions. There's ones that create what we consider the phenomenon of temperature, where energy is translated between particles when they collide. And the other one would be, well, what happens when those particles hit the container that they're in? And that would create a pressure on the container. So they're really focusing on two aspects here, temperature and pressure. And here's the three postulates of kinetic theory. Now, for some reason on multiple choice questions, they really care about the difference between what kinetic theory says and what kinetic theory implies. So if they ask you what it says, then you're going to stick to these three postulates. Matter is composed of small particles, which means that when we talk about matter, we talk about it in a macroscopic way. Large objects that are made, cosmically speaking, that are made out of trillions and trillions of particles. A bottle of water, for instance, would be composed of moles of water, not a few water molecules. But the matter itself, it can be broken down into atoms and molecules. Formula units. 2, particles are in constant motion. There is a certain amount of energy in the universe, and therefore particles all have at least some of that thermal energy, and because of that, they have kinetic motion that's associated with it. And then 3, when we consider collisions, and this goes back to thermodynamics, we're only going to consider the system, not the surroundings. And this statement about particles being perfectly elastic, well, it's 99.999999999% true. Close enough to 100% that we're going to consider it 100% true. There is a little energy lost to the surroundings, but it's going to be negligible under these circumstances. Pardon me. And so therefore, we're going to consider these collisions between particles to perfectly translate energy rather than have some of the energy be lost. And then your book talks about mean free path and talks about the distance that particles in an object have to travel before they create these collisions with each other or with the container wall. And again, in a liquid and solid, because the particles are packed right next to each other, this mean free path is very, very small. However, in gases, there's a large distance, at least cosmically speaking, between the particles. For instance, your book uses this example of oxygen at 25 degrees C, so about 72 degrees Fahrenheit, nice normal spring day. And they would say that the mean free path between oxygen particles is 106 nanometers, so 106 over a billion meters. Very, very small distance from our perspective. However, if you were to translate that, if we were to say oxygen particles, instead of being a few angstroms in size, let's say that they were 6 feet in diameter. and don't get confused on this part. I'm not saying oxygen molecules are 6 feet in diameter. I'm just saying if we blew up the universe to a scale where oxygen particles were 6 feet in diameter, that means if we're telling the average free path is 106 nanometers, that would translate to 6 miles of space in between oxygen particles. So when you think about the air you're breathing, yes, there's only 106 nanometers in between oxygen particles, which is good because if they were 6 miles apart, we would die. But in a cosmic sense, from if you were an oxygen molecule, that distance between particles is huge. I always say that if you're an oxygen molecule, the next nearest oxygen molecule would be at West Windsor Plainsboro High School if we were in South Brunswick High School. Now, the average speed of those particles at room temperature is 1,700 kilometers an hour, about 1,100 miles an hour, which means that the amount of times they traverse that space and collide is 4.5 billion times per second. Now, you're in South Brunswick. The next nearest oxygen particle would be in West Windsor Plainsboro High School. And now you got to transverse that distance each second 4.5 billion times. It is a phenomena that is not intuitive when we think about it, and it is not something that we can relate to. Gases behave, in other words, very, very differently than liquids or solids, which is why they devote this chapter, and they also devote chapters 18 and 19 to just talking about the phenomena of what happens when gases collide with each other. Which factors might affect the number of particle collisions per second? And then they say, all right, we're going to focus on 3 factors. 1, temperature. How much thermal energy do the particles have? 2, the number of particles in a given volume. So in other words, in number 1, if they have more energy, they move faster, they collide more often. Number 2, number of particles in a given volume. If you have more particles in an area, there's less space between them, so they collide more often. And 3, the mass of the particles involved. Now, what they're saying with that is, yes, the more massive the particle, the larger the atom or the molecule generally. However, they're saying, well, we're not going to change the amount of kinetic energy. We're just going to change the mass of the particles, which means there's going to be less space between the particles. Always like this little app. This is the best $1.99 that I've spent in my life, is this little app that tries to emulate noble gas particles. So we have a sample of 16 helium particles And we have a temperature of 100 Kelvin, which means negative 173 degrees Celsius. So very low temperature. And if you look at the particles, they're not all moving at the same speed in this sample of helium. Some of them are moving extremely slow. Some are moving faster. In fact, if we pause this for a second and we highlight that one particle and follow its journey, then as soon as that particle hits another one, it's going to either gain or lose speed. In that case, it gained it, and its speed changes. So at any instantaneous moment, a helium particle may have a almost infinite variety of speeds. Some, again, moving very slowly, some moving much faster. The overall energy of this system, however, is pretty low because the temperature is low. Now, if we increase the temperature, I just increased it from 100 Kelvin to 478 Kelvin. Again, there's still some particles that are moving extremely slow in this sample. The green particle right now is one of them. But the overall amount of energy has increased. And when we talk about temperature, we're talking about the average velocity of a large amount of particles. Notice something else too, that for the most part, these particles move in a straight line. The slower they're going, the less kinetic energy they have, the more likely it is that they are going to curve when they get near another atom. And the reason why is because they have a positive nucleus. The other atom has at least in helium, 2 negative electrons. So they're going to be coulombically attracted to other particles. But as long as they have a lot of kinetic energy, they have enough work energy to be able to maintain a straight line path. Okay. So what if we slow this down then? So we're going to reduce the temperature down to 39 Kelvin. Overall, the samples move slower. The particles, not all of them, some of them a little faster than others. But as they get closer to each other, it is more likely that the particles are going to curve rather than maintain a straight line path. If we reduce the temperature even more, now we can start to see that when particles collide with each other, they don't have enough work energy to be able to bounce off of each other and maintain a straight line path. So this little clumping that you get between particles would be liquefaction. So at a very, very low temperature, even gases like helium start to liquefy. So one of the things that we can do to change the number of collisions per second is to change the temperature. So we'll raise it back up to 500 Kelvin, and now we're getting more collisions. So when a particle hits another particle, the slow-moving particle gains speed, and the fast-moving particle loses speed, and we get what's called a translational collision. So we are translating energy. The overall effect of this in the macro sample is what we call temperature. The higher the temperature, the higher average kinetic energy of the particles. The other type of collision is collision on the container wall, which we'll consider the barrier of this screenshot to be the walls of the container that this gas is in. And if you look at the bottom where it says P, you'll see that the megapascal reading keeps changing, and that's a result of the particles hitting the container wall. So again, we could change the temperature. If we reduce the temperature, now that pressure rating goes down because we're getting less collisions with the container wall, and those collisions do not have as much energy. Another thing they said that you could do is you could change the number of particles. All right, so we can add in more particles. So if we add more helium particles, I'm going to raise it from 16 particles up to 50. Now we get more collisions. If we raise the temperature, we're following our little green helium atom. He's getting knocked around. Energy is being translated. Again, not all of the particles are moving at a high speed, and most of them are moving at the average speed. The other thing we could do to increase the particles would be or increase the collisions rather, would be to change the mass of the particles. Okay, so if we put some more massive particles in there, let's throw in some argon particles in blue. Argon has a atomic number of 18, so much more massive than helium. Now there's less space for the particles to move around. We get more collisions. And I want you to also notice that with argon, are you getting straight line paths or are you getting clumping? So with argon, the more massive particles, there's less work energy. And so the particles tend to curve as they get towards the argon particles rather than staying in a straight line. Of course, if we want things to go in a straight line, we can increase the temperature. 754 Kelvin. Let's see if I can get this going faster. 889 Kelvin. 1023 Kelvin. But even at this temperature, the more massive particles, yes, we get more linear motion from the blue particles, the argon particles, but we still get some curvature. All right. Another thing we can do to change the number of collisions per second is actually to change the size of the container. So if we make the container smaller, so I'm just going to make there be less space between the container. Now we get a lot more collisions. Pressure goes up as we change the container volume size. So as the volume of the container gets smaller, there's less space for the particles to move around. We get more collisions. If we were to take the container and make it much larger, yes, now the particles scatter, but we have a lot of distance for the particles to go before they hit the container wall, so we wind up with less pressure. All right, so we're going to come back to this pressure volume thing in a moment. All right, so summary then, looking at kinetic theory. Here's an image I stole from the internet. All right, so we would say that when we're comparing a solid to a liquid to a gas, we would say that the solids, the reason why they're able to retain their own shape, we know that, for instance, ice is going to have a lower temperature than liquid water, so it has lower kinetic energy in the particles. They say it's highly incompressible. That means that the particles are already touching each other, so it's difficult to, when you add pressure, to get the particles to get even closer. We would say that solids and liquids are not compressible, where gases are highly compressible. And overall, if we compare the kinetic energy levels, we would say, all right, well, in order to make water a liquid, you have to melt it, so you have to add heat. So we're going to have more thermal energy. If we have more thermal energy, therefore we have more kinetic energy in the particles, and they're moving faster. And at a gas, to boil water, we'd have to raise it to 100 degrees C, which is 373 Kelvin. And in order to get boiling, to get gaseous water, now we have to add a lot of energy, so we have very fast moving particles. Now, in order to create intermolecular attractions, the particles have to be close to each other. For molecule 1 to attract molecule 2, you have to have a large van der Waals force. Remember, we talked about that in chapter, well, we didn't talk about it because it was after the schools closed, but I mentioned it in chapter 14, that the difference between solid, liquid, and gas is really not just a result of temperature and pressure, it's also a result of intermolecular attractions. That if something is a solid at room temperature and regular atmospheric pressure, it's because it has high intermolecular attractions between it. Your desk, for instance, your bed, those solids have high intermolecular attractions, intermolecular forces, whereas with a gas, in order to create this free motion in space between particles, you have to have very small van der Waals attractions. In fact, with a gas, since we said a 6-foot tall oxygen particle on scale would be 6 miles away from the next particle, we could say that these van der Waals attractions are almost zero. A lot of times they like to use this image to show the difference between solid, liquid, and gas. It's not really a very good image because, yes, I like that they show the solid where the particles are in a fixed position right next to each other. But in the water example, to be a true molecular example, the particles still have to be touching each other. They just have to be free enough to be able to slide over top of each other and pour. And then, of course, in the last sample, in order for that to be in scale, we would actually need a computer screen 40 yards long, and then there'd have to be 40 yards of distance in between each of those circles. So that's how they depict it. It's not really a very accurate depiction of the difference between solid, liquid, and gas on a particle level. So what do they want you to know here? They want you to be able to fill out this chart. And normally on the FRQ, I would just have you fill out the chart. Of course, in this case, I'm going to have to create multiple choice questions that ask you different aspects of it. So just pause this and go ahead and copy down the chart, and then I'm going to fill it in as soon as you're ready. Okay, I waited. So here we go. First of all, van der Waals radii means the distance between molecules. So in a solid, the particles are right next to each other. So we would say that this value is almost zero. There's almost no space in between the particles. And a liquid, almost exactly the same. The particles are still touching each other. However, there is enough space that allows the particles to slide over top of each other. But for a gas, we're going to say that this van der Waals radii, and I'll just call it R, approaches infinity. Now we have to be careful with this value. Does it really approach infinity? And the answer is no, of course not. There's on average 106 nanometers in between oxygen molecules, and that is not an infinite distance. However, compared to the size of the oxygen particles, again, if they were 6 feet tall, the next nearest particle would be 6 miles away, and that's what they mean by the value of the radius is approaching infinity. Now, in order to create the force between molecules, the intermolecular attraction, we say that it's based on Coulomb's law. So force is equal to K times Q1, Q2 over D squared. So that distance, small distance creates large force. So we would say that the intermolecular forces in a solid are very large. And again, a liquid is not much different. It's a little less than that, but we're still going to call it very large. And the intermolecular forces in a gas, we'll say, oopsie poopsie. Oops. Force approaches, put a little vector over the force. Force approaches zero. Now, in terms of particle motion, the solids are in a fixed position, but they can vibrate. And there's a lot of different forms of vibration. Not only can they vibrate, but they can rotate on their own axis. And the electrons can rotate and revolve. So you actually have about 15 different forms of motion in a solid, because they can vibrate and rotate and revolve in different combinations. With a liquid, you have all of the particle motions that you have in a solid plus one. So we have vibration, rotation, but the biggest one is we also have flow. For a gas, instead of solid, 15 different types of forms of motion, liquid 16, a gas has 17. We have vibrations, we have rotations, we have flow, but we also have free random motion. Okay. Relative particle speed, if you're comparing a solid to a liquid or a gas, we would say that this would be slow, this would be a little faster, and this would be the fastest. And as far as the shape, when they talk about shape and volume, they're talking about transferring containers. As you go from one container to another, if I was to take a solid like ice and pour it from one glass to another, its shape does not change. That doesn't mean the shape is unchangeable. I can certainly take out a hammer, hit a piece of ice, and shatter it. But we would say that as we're transferring a solid from one container to another, the shape is constant. Now, in terms of the amount of space it takes up, the particles are in a fixed position, so therefore the amount of space that they take up does not change as we go from one container to another. With a liquid, the volume is constant because the particles are touching each other. However, they're allowed to flow, So if you were to change, let's say, from a cube-shaped glass to a spherical glass, the liquid would fill the container and take the shape of the container. So we would say that for a liquid, its shape is based upon whatever container it's in. For a gas, the particles are not fixed into position. And as I showed you with that little app, that if you change the size of the container, the particles will spread out and fill up that container. That is something unique to gas. In other words, if I have a swimming pool, 25,000 liters of water, liquid, I can dive into the swimming pool. I don't have to worry about it. The liquid takes the shape of the container of the swimming pool and fills it, as long as we have 25,000 liters of water. With a gas, if I was to take 1 liter of gas from a soda bottle and pour it into a 25,000 liter swimming pool, the gas would spread out and fill up the swimming pool. I wouldn't dive into the swimming pool, however, because the pressure of that gas would be so low and the particles would be spread out so much that, I would injure myself in the act of diving. All right, so that kind of gives us the background for kinetic theory and the difference between solids, liquids, and gas. I'm going to talk more specifically in the next video about pressure and temperature. Thanks.